Hello everyone, welcome to the course on computer-aided drug design. We will continue on the topic of quantitative structure-activity relation, that is QSAR. So if you look at the physico-chemical properties, there are four aspects that needs to be looked at, and that's what we were looking at yesterday also. The hydrophobicity of the molecule, and then you have different substituents, right? So the hydrophobicity of the substituent, that is going to change, electronic properties of the substituent, steric properties of the substituent. So all these play a very important role in the physicochemical properties of the molecule. Okay, so we need to understand these, effect of these, which in turn will affect the activity, so that we can develop a good quantitative structure activity relation. That's the regression. So the substituent can change the hydrophilic balance, the substituent can change the electronic properties, okay, the substituent can change the steric properties of the parent molecule. We looked at Hand's equation. Okay, this is a equation relating various physicochemical properties to the biological activity. Okay, so we have log P, we have the electronic steric factor. So you may start with a simple relationship like activity on the left hand side, and on the right hand side log P we have a parabolic type of relation. It need not be all the time parabolic, but it can be linear also. Then we have the electronic, okay, then we have the steric effect, and this is a constant. Okay, that's the Hansch equation. Generally they suggest, Hansch suggests this. So substituents must be chosen to satisfy certain criteria, a range of values for the physicochemical property. So I need to have which substituent to put into the parent molecule to achieve this range of changes. The value should not be correlated. That's very important. Okay, that's also important. And then of course the rule of thumb, at least 5 structures for each parameter which we are studying. So for example, if you look at the 5, okay, this is related to the okay, substitution. This is molar refractivity. Okay, molar refractivity is related to, like I mentioned in the previous class, the density, the molecular weight, and so on. So look at this, as pi increases, molar refractivity also increases. So obviously they are correlated with each other. They are correlated. As pi increases, molar refractivity also increases. Okay, what is this pi? Pi is related to the hydrophobicity. Okay, so the hydrophobicity increases, mr also, that means volume and density also, so they are correlated. Now look at this set of substituents. So as pi increases, mr doesn't increase, so you can see this, unlike this. Okay, so I need to consider using this type of substitutions in my parent molecule rather than going this way. That's what the conclusion is. Okay, so look at this, there is no correlation between pi, which is related to the hydrophobicity, vis-a-vis the mr, the molecular refractivity. Okay, so negative pi means they contribute more towards lipophilicity, positive means they contribute towards the hydrophobicity of this. Okay, so there is something called a Craig plot, which I showed you in the previous class. This is taken from this particular reference. So you have the electron withdrawing here, electron donating here, we have hydrophobic here, then we have the hydrophilic. So various substituents like chloro, bromo, or NO2, okay, they all lead to increase in electron withdrawing and increase in hydrophobicity. Whereas if you look in this quadrant, we have electron donating and hydrophobicity, these type of substitutions. If you look at this quadrant, we have hydrophilicity as well as electron donating, OH type of substitution, NH2 OH. So if you have, they are more hydrophilic as well as they donate the electrons. If you look in this quadrant, we have CONH2, CN, COOH, and so on. So they are electron withdrawing as well as hydrophilic. So this is a very interesting plot. So we can modify our parent compound by having substituents so that it covers all these 4 quadrants, as well as it covers a range of electron withdrawing, electron donating, hydrophobic, hydrophilic. That's what this plot is all about. Okay, as I said, this is taken from this particular reference. So it allows an easy identification of suitable substituents for a QSAR, which includes both relevant properties, the substituent from each of the quadrant to ensure orthogonality, and a range of values. So we can select lower and higher so that we can cover a big range of values. Okay, there is another approach that's called the tuple scheme. Okay, so we imagine we have a parent compound. We replace the H with the say 4-chloro. So the activity may be increasing, activity may be decreasing, or the activity may be same. Okay, so if it is more, then of course you know that chloro in the 4th position has an effect. So we can have a 2-chloro substitution at the 3rd and the 4th. Again we can have activity increasing, activity being equal, and activity can even go down. Okay, so if it is increasing, then you can think about having fluoro. Okay, and then we can even think of replacing with a nitro, like that, you know. If it is less or equal, we may think of replacing the chloro with the fluoro. Now if you go here, so by putting chloro it's become less, so you can think about having a CH2, CH3, SO2. Like. If it's equal, then we can think about other substitutions. So this is a very interesting a tree-like conclusion we can arrive at. So at each of the substitution we can find out whether it is increasing the activity or no change in the activity or less. So that way, by using this tree, we can slowly make changes to the parent molecule and achieve a highly active compound. Okay, so if you know that you are ending up like this, then you how to change it to this, and so on actually. So that's called a tuple scheme. So I used to decide which substituents to use if optimizing compounds. So we can do 1-by-1 synthesis. Okay, so if the synthesis is very complex and slow, this is a very good approach. If the synthesis is very simple, you may just blindly substitute different functional groups. You can use that Craig plot which I showed you before. Okay, and then synthesize a large number of compounds with various electron donating, withdrawing, hydrophilic, lipophilic. Whereas if it's a very long, slow, complex synthesis, we can use this type of tuple scheme. So after each new molecule synthesis, we can go into the branch of the tree depending upon if the activity is more or less or equal. So this is very useful for aromatic type of substitutions. For an aliphatic also we can look at that later. So what's the rationale here? So we are changing phi plus phi and or plus sigma. Okay, this is related to hydrophobicity, this is related to electronic. So activity increases, so no change, little change. Okay, plus phi and or plus disadvantages. Okay, so we are adding second chlorine to increase phi and sigma further. Replace with the methyl. Okay, so methyl, when we do, we get a minus sigma, but we maintain the plus phi. Replace with O methyl, we are getting both the minus of pi and minus of sigma. Okay, so this is the logic by which it goes actually. Okay, so further changes suggested based on the arguments of pi and sigma and steric factor. Okay, so this is the logic by which or the rationale by which changes are made once you start with the para-chloro and see what is happening. Similar you can do for aliphatic substitutions also. So what you do is, imagine you have a CH3, you replace the CH3 with the isopropyl. So activity can increase, activity can be equal, or activity can be less. So depending upon the situation, if it's more, so what do you do? Instead of isopropyl, you may replace with cyclopentyl. So if the activity increases, you go to cyclohexyl, then you put in CH2 phenyl, okay, then CH2 phenyl, like that you end up with a very highly active compound. But if the activity doesn't change after cyclopentyl, you may go to cyclopropyl. If the activity decreases, so you reduce from pentyl to butyl, cyclobutyl. Okay, this is the logic here. Now when you put isopropyl, there no change in the activity. Okay, that's equal. So what do? We put in Cl2, CF3, CH2, CF2 and so on. Activity may go down or activity may be equal, so you plan accordingly. If the activity is less by putting isopropyl, then what do? You put H, because obviously when you make it more hydrophobic, it's not working. So you go to H, that is remove this, or you make it a CH2 or CH3. Try to make it a little bit hydrophilic, as you can see in this, and hopefully you may get a more active compound than the original parent compound. Okay. So this is how Topliss scheme works actually, and this is ideal if you have very complex synthesis and slow and very time consuming synthetic protocol. Whereas if the synthesis is very fast, I would go and look at the Craig approach and synthesize large number of molecules, substituent molecules, and then test their activity. Okay, so the logic, as I said, if you look here, you put R as H, the activity, that is you're starting, then you put 4 chloro, activity increases, then you put 3,4 chloro, okay, 3 and 4 chloro, and then activity decreases, then you try 4 bromo, activity is same, put 4 nitro, biological activity, it's very good. So you would have achieved a molecule by following this particular logic. Okay, again look at this. We have a R here. Imagine this is your molecule, R starting with H, then you put 4 chloro, activity is less. So what do? You try 4 methoxy, again activity is less. Okay, you have tried more hydrophilic by putting oxygen, but it doesn't. So you try 3 chloro here, activity has increased, so high potency. So okay, so this position is better than this position. So here you do 3 CF3, activity is going down. So maybe instead of chloro you put bromo, again activity is high. 3 iodo, activity is less. So chloro is okay, bromo is okay. So what do? 3, 5 chloro, activity is good. So you found some active compounds, okay, by following this type of logic here. You can also replace with bioisosters. Okay, we talked about bioisosters long time back. So look at these groups of molecules. It's got a pi that is related to hydrophobic hydrophilic balance, so it's negative here because we have O here, that's why. We have a lot of carbons, that's why it's positive. This is becoming more negative. Okay, so sigma for this, look at this, sigma is like this. MR for this molecular refractivity is like this. Sigma for para, sigma for methyl, meta substitution, sorry, not methyl, meta substitutions. Okay, so so you can check it out whether there is any correlation, cross correlation between, and then we can make the substitutions accordingly. Okay, we can select either I want to have a hydrophobic system or a hydrophilic system. You get quite hydrophilic here. So bioisosters, understanding the bioisosterism is very, very important if you want to substitute new functional groups, okay, to improve the activity. Choose substituents with similar physicochemical properties. Okay, look at CN, NO2 and CO methyl. They could be bioesters. Choose bioesters based on most important physicochemical property. Okay, what is very, very important? Is the electronic feature very important, or the hydrophobicity important, or molecular refractivity? Molecular refractivity, as I said, is volume and density. That means the sizes. So depending upon which you realize is important, you can choose bioisosteres based on most important physicochemical. For example, COMe, SOMe, okay, COMe, SOMe are similar. Look at this, sigma P, that is when it is substituted in the para position. SOMe and SO2Me are similar phies, you can see here. Hydrophobicity, not electronic. This is electronic, this is hydrophobicity. Okay, so depending upon which physicochemical property you think is important, we can select. So bioisosters can be very, very useful when you are synthesizing new molecules with different substitutions. Okay. Then there is something called a free Wilson approach. Okay, free Wilson approach. The biological activity of the parent structure is measured and compared with the activity of analogues bearing different substitution. Okay, that's free Wilson. So the equation is derived relating biological activity, the presence or absence of particular substituent. So activity is equal to K1 x1 plus K2 x2 plus Kn and so on, Kn xn plus Z. Okay, C is the parent molecule, and then when I put different substituents, how the activity changes. Xn is an indicator which is given value 0 or 1 depending on whether the substituent is present or not. So if it is not present, we will make K1 0, otherwise if it's present, K1 will be 1. The contribution of each substituent N to activity is determined in the value of Kn. Okay, so this Kn tells you whether its contribution. This is a constant representing the overall activity of the structures studied. Okay, this is called a free Wilson approach. Okay, so what we do, we have say different substituents coming into the picture. So if it's present, K1 or K2 can have a value, otherwise it will become 0. The contribution of each substituent N to activity is determined the value of Kn. Contribution usually is a constant representing the overall activity of the structure study. So what are the advantages? No need for physicochemical constants or tables. Useful for structures with unusual substituents. So we are quantifying the biological effect of molecular features that cannot be quantified or tabulated by hand method. So for each of these complicated substituents, we can find out what its contributions. Okay. So here we need to have a large number of analogues to be synthesized to represent each different substituent and each different position of a substituent. That's also important. Okay, that's a big problem. It is difficult to rationalize why specific substituents are good or bad for activity, because if you look at the other approaches, the Hansch approach, we know sigma, the electronic factor, okay, electron donating or withdrawing effect, hydrophilic or hydrophobic effect. So we can have some rational, or MR positive or low and so on. So we can have different logic for why a particular substituent is giving certain activity. And also the effects of different substitutions may not be additive. That's very, very important. I put in, say for example, 4-chloro, then I put in 3,4 dichloro. The effects may be very different, so it will not be an additive effect. So intramolecular interactions are always possible. So these are the disadvantages of this approach. QSAR and log P. Log P is very important. Aquatic activity of esters, alcohols, ketones, and ethers against stat poles. Okay, this is taken from this reference. So as you can see, as the log P keeps changing, the activity also keeps changing, and these are the various substituent groups actually that comes into the picture. CH3OH starting from that, and so you keep on adding CH3, so it's becoming more hydrophobic. Okay, activity also has become 1.05. So log P plays a very important role. So we can plot, same reference, we can plot a log P versus activity. So as it becomes more hydrophobic, the activity also increases. The R square, which is a measure of the fit of the data. So this is the QSAR equation, straight line equation. X is the log P here, Y is your activity here. So the regression coefficient is 0.88, and R square, which is a measure of the fit, is 0.77, which indicates a good fit. Okay. So this is for ketones. So for a subset, only alcohols. So if you take only alcohols, you may have a second order or a quadratic relation, so you can see R going up much further. Okay, so as I mentioned long time back, QSAR is very good if you have a set of molecules. When you extend it to other molecules, sometimes it might not work actually. So alcohols alone, you can see a very good relationship. Okay, of course this is also reasonably good. We have taken ketone, ethers, tadpole, alcohol, esters also. But if you take in more hydrophobic substituents, then the regression relation could be very poor. So look at this log P, hydrophobic. This is very hydrophilic. Methanol, propanol, isopropanol, ethanol, okay, phenylalanine, imidazole, diethylamine. Now this is becoming more hydrophilic, so it's more positive. Benzene quite high, pentanol quite high. Okay, log P is a very important thing because log P, as we have been talked long time back, it tells you the solubility, it tells you the GI absorption, it tells you the HERG, it tells you the plasma binding, it tells you the membrane penetration. So log P is dependent on so many. Log P affects so many different parameters. Polarizability. It's called atomic polarizability, ease of distortion of electron clouds. Okay, sum of van der Waals equation. Okay, so if you remember van der Waals equation, A by R raised to the power 6, B R raised to the power 12. Okay, I hope you remember that. Molecular refractivity, of course, defined before also. Molecular refractivity talks about the size and also the polarizability. So molecular weight divided by the density. Okay, that's called the molecular refractivity. This is another important descriptor. This is another important descriptor. This is another important descriptors. They will come quite a lot in many of your QSAR equations as you go along in your activity. So it's different substituents. Okay, volume, molecular refractivity. Okay, electronic feature. Okay, sorry, this is not electronic feature. 5 represents the hydrophobicity. Okay, and then this is the number of rotatable bonds. So all these can have effect on your QSAR relationship. Okay, let's look at some simple systems also. Okay, now if you know, this is called a nalidisic acid. Okay, this is a commercial antibiotic. This was discovered a few decades back. This is given for gram-negative bacteria, mainly for urinary tract infection. It has reasonably weak good activity. The structure activity studies have shown that the pyridone ring A, this is the pyridone ring A, is essential for activity, and this ring can be changed. So we can have this kept constant, and we can have these things changed quite a lot. Okay, so we can have a large number of compounds synthesized following this approach. Okay, so many compounds were synthesized by modifying the ring B. Okay, they were found to be almost 500 times more active than the original nalidisic acid, which was originally discovered maybe about 15-20 years back. Okay, and the novel compounds are much broader antibacterial activity than the original. Okay, so 1983 Norflox, you can see this, the ring A is kept constant, it's changed like this. Offlox, ciproflox, tosuflox, inoxazine. So all these are new molecules that were synthesized starting from the original nalidisic acid. Okay, as you can see here, and you can see that this portion is kept constant, and you make a lot of changes on the other B ring, and you end up with very highly active molecules. Okay, and more potent and more wider range of activity. Okay, that is the beauty of understanding the structure activity relationship. Okay, that's very, very important actually. So this is taken from this particular reference. This is a very interesting picture. Okay, Taxol, okay, or paclitaxel. This is an anti-cancer drug. Originally, it was found from a natural product called yew trees. It's found in some European and also in Himalayan region. This tree is found. The original molecule, the anti-cancer property molecule, had poor bioavailability. It had very poor water solubility. So the second generation, a lot of changes were done to the parent molecule to improve the water solubility, and then later on salts of this was also made to improve its water solubility. So the current Taxol has better bioavailability and water solubility unlike the original. So how this was performed, because of the understanding and the importance of each one of the functional groups and the positions. So look at this. Removal of or modification of OH group reduces activity. Okay. Hydrophobic interactions between these groups may correlate with the activity. That means you can have two benzene rings, so there could be a benzene stacking. A ring contraction gives products with reduced cytotoxicity but similar tubulin polymerization activity to paclitaxel. Opening of this ring gives inactive product. Contraction of the C ring to a 5-membered ring reduces activity. Deacetylization, that means remove acetylization, gives less active product. So by knowing what are the important groups that are necessary for activity, what are the groups that might not really have a play in the activity, we can develop new structures by modifying those places. Reduction of the C9 carboxyl group increases to an alpha OH group increases activity slightly. Removal of the 10 state or deacetylization to form 10 deacetoxy derivative do not make major change in activity. Okay, so these positions do not have much effect. Acylation reduces activity slightly or significantly depending on the acyl group. So you see some locations have a major impact on activity, some locations have minor impact on activity. So one with the medicinal chemistry, synthetic chemistry knowledge can come up with large number of new derivatives and check out their activity, because as I said, the original paclitaxel has poor bioavailability and poor water solubility, and although changes have been made to come up with new generations of paclitaxel, still there is a lot of research that could be done in coming up with new structures. So this slide was taken from this particular reference. Okay. So we will continue further on this topic of QSAR in the next class as well. Thank you very much for your time.